So the first program I wrote as a child, probably in BASIC or Logo, had bugs. And the ones I'm writing now in Rust, Go, and Python most likely have bugs too. And I've had lots of opportunities to wonder, could we write software that has fewer bugs? I think that's the reason I got so excited about Rust and remain so excited, that it's practical for the kind of programs that I like to write and very approachable, but it also systematically eliminates whole classes of important bugs. The reference system excludes most pointer and memory management bugs that I've encountered in C, but also the aliasing bugs I've seen in Python and Java and null pointer exceptions. Compiler warnings like must use, never read, and dead code also flag many bugs. And expressive type systems help make illegal states unrepresentable and shift more bugs to compile time. Not only does Rust save you from some bugs, it also saves you work writing tests that you might need to write in programs in programming languages with fewer compile time checks. But semantic bugs can still get through in Rust. As the Rust book warns, safe Rust can still delete the production database. So what could we do to reduce the risk of introducing bugs in new code or to flush out existing bugs in a code base? Well, there's a lot of approaches, but one technique that software engineers obviously rely on a lot is to write some tests. Tests won't catch everything. Tests, as normally conceived, won't be very effective against rare race conditions or edge conditions. Tests won't tell you you're solving the wrong problem. Tests won't tell you your security protocol is weak or that your sharing feature introduces a privacy risk. For those, there are lots of other interesting tools that we can use. But for many types of algorithmic correctness, we look to write tests. Except, unfortunately, I do write tests and I still have bugs. Perhaps, like me, you've looked at a bug and you've asked yourself, how on earth was this not caught by the existing tests? Sometimes we simply just don't think to test something that actually is important. In particular, it's really easy for us to focus on the happy path or the main point of the code and to forget to thoroughly test the edge cases or the kind of secondary functions that might still be important. It's also possible for the test itself to be buggy in a way that causes it to pass when it ought to fail. In particular, sometimes we only write 95% of the test. We forget to check thoroughly the results of what happened when the test was run. I think human psychology is so interesting, and often we're grappling with the limitations of the human brain and human mentality when we're writing code or writing tests. When the requirements or the problem domain is very complex or the existing code is very complex, to make progress, we have to think of a simpler model to understand what we're trying to do. But then it's really easy to get captured by that model, and it's hard for us then to look for ways in which the model is correct or is incorrect, in which we've oversimplified the problem and missed something important. It can also happen that the test was actually totally fine at the time that we wrote it, but after that the program changed and became more complex or gained more paths or more options, more abstractions. And so later on the test still passes, but the test doesn't really have teeth to find the bugs that it once would. So, as I said, although there are some kinds of bugs and problems in software that can be very hard for tests to catch, I do still think a significant fraction of bugs that make it through review and into production could in principle have been caught by tests, but the tests weren't quite up to the job. So I think it'd be so nice if we had a tool that would point out to us in what places are our tests too weak or incomplete. Let's think about the process that happens when we're writing a test for some software. We have, at the top, an idea of what we want the program to do, and the result is that we want at the bottom that the program should do that thing. And we use tests as a kind of lever or mechanical advantage to try to show that there's a strong connection from what we want to what the program actually does. And so when we're writing tests, we have to try and make sure that those arrows in that chain are both strong and robust, so that the connection from top to bottom is also strong and robust. And more specifically, we have to make sure that, firstly, the tests capture every property, every requirement that we care about, that the tests actually would fail if the program was incorrect. And thirdly, because of course we can't exhaustively test any non-trivial program, We have to try to make sure that the tests are still general enough and representative enough that they're likely to be a good indication that the cases we didn't specifically test are still working correctly. So one way to think about finding weaknesses in our test suite is to reverse this bottom arrow, right? So to ask the question of what behaviors does the program have that are not checked by any tests? Those aspects of the program, at least with regard to tests, are kind of flapping in the wind, and they might do anything, and the test suite won't tell us about it. We could change the program later in a way that introduces bugs. Maybe somebody who's not so familiar with the code tries to change it, and they introduce a bug, and the tests don't tell us about it. Or maybe the code is actually buggy today, and the tests aren't helping us know about that. Or maybe the code is redundant or obsolete or simply unnecessary for the function of the program, and that's why there are no tests that check what it does. And it's also totally possible that the code is totally fine and there are just no tests, but are we really comfortable that it's going to stay like that? So here's an overview of the project I'd like to tell you about today, cargo-mutants. Essentially, it automates the process of checking whether there are any behaviors in your program that are not checked by the tests. More specifically, these steps: first, make a copy of your source tree, then mechanically insert a synthetic bug by changing or deleting some code, as if you got a PR from somebody who doesn't really know what they're doing, they're just kind of randomly changing their code. Then build it. If the tree fails to build, then we can't run the tests, so it's kind of inconclusive, we just carry on. If we can build it, then run the tests. And because we just injected a bug, we expect and hope that the tests will fail. If they catch it, that's great. That's a positive sign about our test coverage. If they miss it, then we call that a missed mutant. That's a thing we're going to think about later, and then essentially repeat this over and over for every synthetic bug that we can think of to insert into the program. So here's a small example that kind of naturally occurred in my own code that was caught by cargo-mutants, and where it found not only a gap in the test, but actually a real bug. So I was writing some code that talks a network protocol, and it gets the so-called Unix mode bits on a file system entry, and it's trying to work out over in here. Is it going to work? Try to work out if that thing is a file. If you hit L in Google Sheets, you get a cute laser pointer for your cat. Try to work out if it's a symlink by doing some bit math in octal numbers. And I wrote this, and you can see I wrote some tests because I'm diligent, so I check a particular value that is a symlink, and I also check a symlink from the local file system. And then I ran cargo-mutants on it on the bottom. And it's telling me in the line in yellow that if I just replace that whole function with the expression true, so if the function just always returns true, the tests all still pass. And like, the point of this function is not to just always return true, so something is wrong here, right? And I think this is, a small, slightly embarrassing example of the human mental limitations that I talked about before, that we're thinking about finding symlinks, and we're not thinking enough, I was not thinking enough, of the fact that we also want to find things which are not symlinks. And this actually didn't manifest in the larger program that I was calling it, because it was a series of like chained ifs that essentially only arrived here, if we'd already checked if it was a file or directory. Anyhow, so I forgot to add any tests that checked that this should ever return false. So let's fix it. I added a test. The test is pretty much what you would expect. Check what this function does if you give it the permissions of a directory. And I found that in fact the octal math was wrong, and it should be like that. And you run cargo-mutants again, and it says it's all good. So it's a tiny program, but it was a nice example. So here's a screenshot of it churning away on a larger example, which is the semver crate that understands semver tuples and lets you say, is this compatible with this requirement, and so on. I picked this as an example because it's a good crate, it's widely used, it's like relatively simple to understand, And it's a kind of thing you would expect that it would be very deterministic and testable, right? There's no weird side effects. But it's also not my crate, so it's hopefully an unbiased example. And it's finding a bunch of findings, right? So a bunch of functions that we could replace with a single value, and the tests would still pass, and then a bunch of other changes that we could make, tests that still pass. And I think this is really typical of what I tend to find on high-quality crates, like this, using an example, and not to say semver is a bad crate, and then just the opposite, this is a good crate, but when you run it, it still finds a bunch of gaps in coverage that are perhaps interesting to look at. For instance, the one about hash here, so this is like the implementation of hash on a data type. This is used when you store it in a hash set or something like that. If every object hashed to the same value, the tests would all still pass, which might be at least a performance problem. Some of the others are showing if the debug impl for this type did nothing, like if the debug impl was all the empty string, the tests would all still pass. So you can, you can decide, if you're the author of a crate like this, you can decide, do I care? Maybe you don't care about testing debug. Maybe you think it will be obvious if it's wrong. I don't know. Maybe it'll be confusing if the debug implementation is buggy. But there are things to think about, right? And they are parts of the library API that potentially your users would care about, working as you intend. The other really interesting one in this, I'm not going to go through all of them, but the other really interesting one is that if you replace the serialize and deserialize implementations in this with nothing, so like it ignores all the data from the file, the test still pass. And when I looked in the crate, there are no tests for SERDI. It's like implemented and we assume it works. So this is like a reasonably widely used crate in Rust. It's a perfectly good crate. When I looked at the implementations, they don't look buggy. They all, like I assume they all work properly, but they're not tested. So this is like an example of the kind of findings that you might have running it on code that basically works. So more broadly, you run cargo-mutants, it gives you a bunch of findings like this. What do you do with them? The thing I would recommend, first of all, is to just kind of skim the list, right? And just see, if you recognize function names or types or file names in there, is that code from your experience with this code base that you would expect would be tested a lot? Is it code that you think like matters a lot that it be correct, or is it maybe ancillary stuff that you don't care about so much? See if anything sticks out as surprising. And then as you pick some findings to think about in more detail, you could ask yourself, is the mutation actually incorrect? Like, would it be wrong for this function to always return true? Would it be wrong for this function to do nothing? And then, is the original code actually correct, right? So probably often it will be, but maybe not. And is there a test that you know of in the code base that should have caught this kind of bug, right? If it didn't, then why not? And if there does seem to be a test gap, then should you test a larger category of stuff where this is, pointing to a gap, but you actually need to consider some larger situation. And of course, like as I said before, does it matter to test it? These are the findings from cargo-mutants are framed as things you might think about. It's not, the computer is not the boss of you. You can decide what you think is important to test. It's just information. Some things maybe don't matter as much. And also, unfortunately, some things really matter, but are really annoying to test deterministically and hermetically. There might be something that's important to performance, and if there was a bug in it, performance would regress a lot, but perhaps it's really fiddly to write a test, and you have to decide that you're just going to rely on benchmarking or some other technique to make sure that it doesn't break. But then maybe that's at least interesting information, right? To realize that your performance could regress a lot, and cargo test won't tell you that something broke. I also want to emphasize in this, it's important not to, you could say, overfit your response to the particular findings, because cargo-mutants is generating synthetic bugs that are meant to be kind of signposts to things to think about, but at the end of the day, the goal of this is to catch and prevent real, actually occurring bugs, not just the synthetic bugs. So as an analogy, you want your body to develop immunity to the actual viruses that are floating around in the world, not to the kind of synthetic, simplified virus that you get in the immunization. So in the symlink thing, you know, I could have written a test that says, is symlink of 0 is false, and that would show that at least in one case it returns false, but that's not really the thing I care about. What I care about is that it says a directory is not a symlink. So having shown a little about cargo mutants from the outside, let's dive in a little bit to how it's built and what kind of mutants it can find. So the most interesting part of the code is generating synthetic bugs. And the goals for this, like, first of all, we have to generate valid Rust that builds. You know, if it doesn't compile, we can't run the tests. But then after that, the most important thing is to try and generate, I really try to generate mutants that are likely to point out real gaps in tests. So I like to be relatively realistic for things that might happen as a result of a mistake, editing code, or, you know, a bad copy paste, or a bad LLM suggestion or something like that. Also, we want to generate mutants that are not too repetitive, because that would just be wasting computer time and wasting your time looking at it. And I also thought it was really important that they be deterministic from the source tree. You run the same thing again, you get the same result. So there's no like randomness in what it chooses to mutate. And it turns out, and there's a lot of previous research on this, it turns out that making reasonably small localized changes are like reasonably realistic for what might happen in actual bugs, and are also easy to generate and easy for the programmer to understand what the finding is telling you. So diving in a bit more, the implementation of it essentially uses two great crates to understand what's happening, or a whole bunch of great crates actually, but cargo metadata to understand what's in the source tree, and then the syn package to parse Rust source code. This is such a nice thing about working in Rust compared to C++. So you can, or whatever, you can just like import this thing and it parses Rust, you know, correctly, and you can go ahead and poke at it. So I think there's a lot of potential for people to write interesting other tools that introspect on Rust source code. Syn gives us the source tree one file at a time, but it doesn't understand how the files fit together into a crate. So I had to implement some stuff to like understand mod statements and work out which file to read for the mod. And there's actually a surprising number of hairy edge cases in that. Then it gives us an abstract syntax tree, and then we walk across that using a visitor pattern like shown in the code on the right. You don't need to understand all of it, but essentially this is an example of it saying, if we see a not operator or a unary negative operator, we could try mutating it to just nothing. So just like delete it, that'd be a good thing. And it matches, it kind of pattern matches this way various different things that can occur in the Rust source tree. The mutation, and I think there's like scope to add more mutation patterns later on, but the most fruitful one has proven to be just replacing the function with the value. Again, like the example of saying, what if this just returned true all the time? Or think about functions in your tree that might return a result, but what if they just said it was okay, and they were like just very lazy and didn't do anything. They just said, it's fine. The AST shows us the return type, which is another kind of attribute of Rust that turns out really nice. You know, function return declarations are typed. And based on this, we have some heuristics about different types that can occur in Rust and what would be good, essentially good guesses about what would be a value of that type that would probably compile and probably be wrong. So for integers, we just try, what if the function always returns -1? What if it always returns 0, et cetera, et cetera. And obviously, often types in Rust are nested, like this one at the bottom, in which case we kind of blow out the tree of all of the combinations of the different nested values so that you can get what if it returns, you know, okay of some of the vec of an empty string. And this generates like a number of values for each function, but not a kind of excessively massive number. So I've been working on this for a few years as a side project. I've been running it on my crates. I've been running it on like interesting community open source crates. Other people have been running it on their stuff and giving me feedback or impressions. I've generally found that getting to 100% mutant coverage is a bit of work because it points out gaps in your test suite that you could suppress them and say it doesn't matter, but at least some of them, I think, oh, that does matter. That is kind of bad that that thing is not tested. I'll try and add a test. Then you have to add a test or maybe refactor the code to make it more feasible to test, and that can take a little while. And occasionally you find a real bug. I think mostly you find test gaps, but occasionally there is a bug hiding in the gap. The most difficult cases in my experience have been when there is a test, but the test is flaky. And I think flaky tests are always bad in a bunch of ways. I want to fix them, but I just had not noticed until cargo-mutants ran that test hundreds of times, and then I noticed that something was wrong with it. And sometimes it can be hard to work out why the test is flaky. I found it works well to turn it on for one file or one module or one crate at a time, maybe starting with the one that you feel is the best tested at the moment, where you might hope that it will kind of give you a thumbs up immediately, or the most important to test, or maybe the easiest to test. So if you have a project where some of the tests are really more like integration tests and they talk to a database and they're very slow, maybe start on the crate that is like a key data type that's pretty, straightforward to test. Cargo-mutants got up to 100% coverage, so nothing is missed in it today. CI says, like, for any PR to merge, there should be no new missed mutants. And once you get to that level of coverage, I've found it's pretty easy to stay there because you're just always dealing with a few little kind of, like either zero or just a couple of new missed things to think about on each iteration. I'd love to hear feedback from people who try it on your stuff. I've generally found some crates have non-hermetic tests, meaning they don't, if you run them over and over again, they won't necessarily pass every time. And there's also lots of interesting cargo edge cases. Like, did you know you can put a path attribute on a mod statement and it can point outside of your tree anywhere else in the file system? That's kind of surprising. That works in cargo-mutants now. So cargo-mutants, over and over again, hundreds or thousands of times, does an incremental build and then runs the tests. So, Rust is not famous for fast builds, and some people have tests that might take, minutes or more. So it can be a lot of CPU time. But happily, there are a few things we can do to fearlessly parallelize and speed this up, because each of the tests of each mutant is independent of the others. So first of all, Cargo, Rust and the test framework are pretty good at spawning lots of threads, although towards the end of the run, they can have stragglers and the cores can go idle. So cargo-mutants can run multiple cargo things in different directories at the same time to soak up more of the cores and keep your machine busy. And then because the mutants are deterministic, we can spread across any number of parallel workers in the CI, and they each just handle one shard of the total work. So some concrete numbers on performance. So cargo-mutants itself, 11,000 lines of code, I guess it's including the tests. I guess you'd say kind of a small, medium crate or something like that. Building it takes 12 seconds. Running the test suite takes about a minute. It produces 575 mutants looking at its own source code. And testing all those mutants takes 15 minutes. So it's not 575 minutes. It's a lot faster than the worst case, but a bit of time. As I said, I run it on GitHub PRs, and they, with 10 wimpy machines scaled out, about 10 minutes to run all of the tests. So if your test suite takes an hour, it might be tough, but if it's less than that, it might be pretty feasible. Okay, so people will often say, this sounds a lot like coverage testing. It's kind of similar. Coverage checks that the code was executed, whereas mutants checks that a code depends on the result of running, a test depends on the result of running the code. So in the symlink case, the code was executed, just no test checked what it returned, and that's a difference. Mutants tells you exactly the bug that was missed, which can sometimes be easier than trying to work out why particular code was not executed under coverage. The downside is mutants is running the tests over and over again, so significantly slower. You could very reasonably run both and use them as complementary things. And that just to wrap up, mutants, people often ask, this is like fuzzing or property testing. Fuzzing and property testing are wiggling the input to the tests to try and find bugs. Mutants is wiggling the code to try and work out whether the tests are any good. So again, complementary. So yeah, thanks very much for coming. I hope you found this interesting. It's pretty easy to get started and try just to install it and run it in your crate. If that fails, or if that, for some reason is not giving you interesting output, please let me know. Very feasible to just try it out and see, if you think the findings are interesting. And if you do, then I think pretty easy to turn it on in CI and keep it up to there. So yeah, I'd love to hear questions offline, feedback from using it, anything like that.